and share my screen and come over here. And so yes, good afternoon, everybody. Welcome to data mining. If you don't have them yet, there's notes up front. There are unfortunately no staples in them. Should be 6 sheets of paper numbered 1 through 12. In the class webpage, getting these electronically, I've added a new folder, 02, learning from data right here. Clicking that, and it's the notes1.pdf file. It should be 6 sheets of paper. Unfortunately, no staples. Today in class, well, let's see. The first 3 weeks in class, we've gone over the PageRank algorithm and midterm this coming Thursday on PageRank and the last 4 sets of notes. And then we'll talk about that here for maybe 5 or 10 minutes. And then today we'll be starting new material, starting with the stuff from the actual book, the Learning from Data book, and going over the first notes for that today. And the programming project, again, sort of nominally due last night. Anybody collaborating in basically any form with anybody else gets extension until Tuesday at midnight. Okay, midterm info. So I mentioned this last time, but let's talk about it again. This Thursday is when I will be, let's make that bigger, posting your midterm, and you'll have until Sunday, so about 4 days to complete it. There's no time restrictions at all, no restrictions on what resources you're allowed to use, so untimed. You can use any non-human resources, that's the only restriction. You can talk to your dog if you want, but you can't talk to a person. So notes, books, internet articles, computers, feel free to use all of that stuff. And when I mean talking, like not talking to other people about it, I really mean not talking to other people. So in particular, some examples. So obviously bad behavior, something you can't do. It'd be like sharing answers with other people. But even more subtle behavior that I'm asking you not to do is just like offhand comments to your friends about, oh, problem 6 was so hard on the quiz or on the midterm, because that leaks some information about what the answer to problem 6 should be, that if you didn't spend a lot of time on that, then maybe somebody will go back and spend a lot of time on it. Or even something like just asking somebody, have you completed the exam yet? I'm going to ask you not to ask questions like that to people until after Sunday. After Sunday, after the due date, after it's all submitted, then you can talk about it however you want. If you do have questions about the exam, email me those questions rather than posting them on GitHub, and I'll do my best to clarify the questions. Again, the format of the midterm, 15 points total, 10 true or false open questions. You want to make sure that you pay extra attention to those, because you'll get a -1 penalty for answered questions that are answered incorrectly, and then 5 free response questions. Some last other notes. So normally I'd have Friday office hours where you could come and ask questions about anything in the course material. This week, you won't be allowed to come to office hours and ask questions about the course material, since it'll be in the middle of your exam. But if you all would so we're not going to have an in-class review session, but I'd be happy to organize or to have an out-of-class review session sometime on Tuesday in the afternoon. But my expectation is that if you all want that, then you'll organize it and just tell me when and where to show up, and I'll show up and answer any questions or help people however I can. Also have normal office hours on Tuesday as well, for people to ask questions. Any questions about anything related to the exam? Yeah. Submission will be through Sakai, yeah. I'll be so I'll post the PDF on GitHub. I'll have an issue with the link to that, and then there'll be a Sakai assignment where you upload your completed PDF. Or if you'd prefer, you can deliver it in person if you want a printed out thing and write it out in person. Either way is fine. Any other questions about the midterm? Everybody's 100% ready for it? Any questions about anything administrative related to the class? Yeah. Question is, on the midterm, can you lose points on the free response questions? Can you go negative? And the answer is no, no matter how bad of something that you write on the free response questions, I will not take away points. I will just not award points. But on the true, false, open questions, if you put something wrong, then you'll lose a point. Maybe one last thing about the midterm is just a reminder that the final exam in this class, so we have 3 midterms, all will be worth 15% of your grade. And then the final exam in this class, the final exam will be an oral exam. Everybody will have to schedule an hour time slot with me over the finals time period to do that. And one of the things that will happen is that if your final exam is greater than one of your midterm scores, then I'll replace the midterm score with the final score. So if for whatever reason your result on this midterm is not what you hope it to be, you'd still have a chance to improve it. Any other administrative sort of questions? Okay. So today we will talk about new material. And I realize since there's the midterm coming up, everybody's mind's like, oh, who cares about this material? I need to panic for the midterm. Part of the reason why things are scheduled the way they are is that a lot of things that we'll be talking about today will help hopefully clarify or reinforce some of the concepts related to PageRank and runtimes. And so we'll see that today we're going to be building up today and Wednesday into this new algorithm called the Perceptron learning algorithm. And we'll be making some comparisons to PageRank as we go along. And so there'll be some opportunities for review-ish things kind of nestled in there. Again, we're looking at this new textbook. Chapter 1 is what we're going over. It's called the learning problem. And so let me make this a little bit bigger. Maybe one of the nice things about this portion of the course is that there'll be a lot of extra material that you can reference if you want to see more things. So besides the textbook itself, the author of the textbook, the Caltech professor, they use this at their Caltech class, has all of his lectures from the textbook online. You can take a look at those if you would like to. So you have, if for whatever reason something in class doesn't fully click, you have those other resources, the book and those videos. Okay, so our problem setup here. Now that we are learning from data, there's gonna be a lot of notation, especially at the beginning part of today. And the goal, the thing that you should hope to take away from today is getting some intuition about that notation. If that's where you're at after today, it was 100% success. So the idea of this problem here, and okay, before we get started, one last meta sort of thing. Again, another one of the goals of this class, big picture goals of this class, is to prepare all of the data science students for the data science capstone project. And this problem right here, problem 1, actually comes from a previous data science capstone that was actually a fintech practicum through the econ department, which is the same thing as like the data science capstone. We're working with Wells Fargo, and Wells Fargo was trying to improve their ability to give loans to customers. People apply for loans, and you don't want to give a loan to just everybody because then they'll spend the money and they can't repay it back. So how do you pick the right people to give loans to? We'll be going through, the book actually uses that exact example here. And so we'll be going through this, describing how all the notation from the book fits into that problem of assigning loans. And again, on all of these problems, all of these notes, I've tried to highlight like where exactly in the textbook you should go if you want to, if you missed something or something didn't fully click and want to review that material in more depth. So this is section 1.1.1 is this motivation from the textbook. So in this case, so we're making loans. So we have some input into our algorithm where our algorithm is trying to determine whether we should provide loans or not. And the input's always going to be the X variable, and the output of our algorithm from now on is always going to be a Y variable. And the semantics of these two variables in this particular case is that X will be all of the things that, that we can somehow use in our loan decision-making process. All the info for determining whether to give a loan. And then the Y is going to be whether we actually give the loan or not. So the stuff in red here is all just like informal, what the, again, the semantics of these variables is supposed to mean. And the stuff in red is very particular to the bank loan problem. This X variable is always going to be, so contained in R to the D. So it's a vector, a D-dimensional vector. And at least at the start of this class, the Y variable is always going to be contained in a set with just two elements, +1 and -1. Here, the semantic meaning of this +1, we can think of it as should give the loan, or alternatively, maybe we would make money if we give the loan. Or another way of possibly thinking about it would be the person is able to repay the loan. And then the -1 is just all the like the opposite of that. That either we don't give the loan, or we would lose money if we gave the loan, or we're not able to repay the loan. All things that are sort of semantically essentially the same thing for this problem, and all being formalized is just represented as either a +1 if it's a good outcome, or a -1 if it's a bad outcome. And in this case, for our inputs, our X's, let's think a little bit more about what types of inputs we might have. So it's a D-dimensional vector. So our maybe like X0 position, the 0th position, the very first element of our vector, that might be the total assets of the person. So if the person already owns a home and a car, then they have a lot of assets and more likely to be a good candidate for a loan. X1 might be the total debts. If they already have a lot of loans that they've done with other banks, then maybe less likely to want to loan to them. X3, their annual income. Maybe x4 we could say is 1 if they're married and not 1 if and 0 if they're not married. Depending on your particular jurisdiction in when giving loans, it may or may not be legal to have some information like this inside of your X input variable. But in general, if you are legally able to know if the loan applicant is married, married people tend to have more stable jobs, more stable lives, more ties with the community, so more likely to pay back loans. So it's useful information to use if you can. Any questions about any of this problem setup so far? Question is that sometimes for our outputs, other formulations might have like +1 and 0 instead of +1 and -1. And these two sort of formulations are 100% equivalent to each other. Sometimes people will also say just like true and false. There's no real reason. In our case, actually, it's not even going to be particularly mathematically convenient one way or the other. That's just the convention that the book happens to choose. But just the real important thing right now is that Y is binary. 2 options. And so sometimes this problem in general, where you have an input and an output and trying to assign outputs to that input, is called classification. Let's go back to green here. And in this particular case, it's binary classification because we have just these 2 outputs, but you could imagine more possible outputs. Classification or binary classification. Good question. Any other questions about the problem setup? Okay, the book talks a lot about the difference in this first chapter. It talks a lot about the difference between what they call learning sort of problems and design sort of problems. When I was talking about these features up here, I was making some sort of guesses, kind of informed guesses about like, oh, people with a lot of assets, probably good candidates to loan things to. But we're not really interested necessarily in the actual semantics of any of these things when we're doing the learning problem. We're not trying to somehow predict in advance which one of these things are going to be better. Instead, we're going to also be given a data set. Which the book calls a script sort of D, like that. And the data set has n of these examples, x1, y1, up to xn, yn like this. So the n right here, total size of the data set. And something that's particularly confusing here at first is that you'll notice up here, I'm using subscripts on these x variables. And down here, I'm using subscripts on these x and y variables. But these subscripts actually mean totally different things in these 2 locations. Down here, when I say like x sub 1 or x sub n, this subscript is telling me which of these data points I'm looking at. So it's like which x. Up here, when I have these subscripts like x sub 0 or x sub 1, this is not data point 0 or data point 1. This is which index into x. Here, the subscript is the subscript into x. Vast majority of times in this book, when you have a variable that's being subscripted, it's talking about which one of those variables. But occasionally they use the same notation to actually index into the variable, and they just expect you to be able to tell from context, is this thing a vector? Then we're talking about which vector it is. Is the result a scalar? Then we're talking about which index into that vector. Couple more last bits of notation. At this point, we're assuming that all of these y values are created according to some formula like y sub I equals f of x sub I. Again, these subscripts right here you should be thinking about which data point I'm referring to. So this is all referring to all the data points. There's this function f that converts from the x's into the y's. In this f function, in the book, they sometimes use the words, this is an ideal function, or like the ground truth, or just the truth function. They also, outside of the book, you sometimes hear people talking about this function as like the God function, or the Bayes function. And the idea of this function is that like we don't know necessarily who is going to be a good candidate for loans or not. But if whatever higher power, whatever ultimate force in the universe you do or don't believe in, if there was one of those things and it was deciding who to give a loan to, that higher power would be using f. Like whatever the most optimal thing to do would be this f function. So somebody who knows something that knows everything about somebody's life, knows everything about all people at all time, all the possible economic conditions, whether we should give a loan or not give a loan based on these particular features that we had. So in the book, talks about it the ideal or the truth function. Other resources you'll see talk about it as the God or the Bayes function. And then last thing, our goal. So we can't know this f function. We can't know this f. It just exists out there somewhere. It's what the universe is using to determine whether people should get loans or not. But our goal is to find some function g that's approximately equal to f. And so what this approximate means is something that we'll be talking a lot about throughout this course. But we're going to be using a lot of probability, getting into statistics to describe this. At this point, we're not going to, or these first few lectures, we're not going to be talking too much about at all about probability and statistics. Instead, we're going to be looking at this algorithm called the Perceptron algorithm that turns out to find reasonably good G's for us. And we'll be starting off talking about the runtime of this Perceptron algorithm. So that'll be how it ties back into PageRank. PageRank, again, talking just about the runtimes of things is what we're focusing on. Any questions about the setup of this problem or any of this notation? Yeah.
Can you say that the ideal function has like a 100% accuracy?
So yeah, the question is, does this ideal function have 100% accuracy? This begs a little bit of notation about what exactly do we mean by accuracy, which we'll talk about later. But yes, like no matter what sort of measure of goodness that you have, whether it's accuracy or something else, this has to be like perfect, 100% perfect. Okay, we'll be starting this, again, using this Perceptron algorithm. And anytime in machine learning or data mining, when we talk about an algorithm, there's this phrase, that hypothesis class, that comes up. So we'll start talking about this Perceptron hypothesis class. There's going to be maybe, I don't know, lots of definitions that will hopefully tie in together at the end once we've defined them all. But if they're not fully clicking instantly, then that's okay. In the book, so again, now it's section 1.1.2, this hypothesis class is defined as h of x equals the sine of the sum from I equals 1 to d of w sub I x sub I plus some b value over here. W is also an r to the d vector. And it's sometimes called the weight vector or parameter vector. And in general, people talk about W, the weights, the parameters, the weight vector, parameter vectors, all those terms sort of interchangeably. And here, when I say h of x equals to this, notice that there's no like W over here in this h of x. So this is really not just a single function. This is a family of functions or a class of functions. When we have this term hypothesis class, the book doesn't really formally define exactly what they mean by hypothesis class, but it's really a family or a set of functions. Set of functions. And again, we know that this is a set of functions because there's this W parameter right here, W, also the B, that's not included anywhere in the definition or the sort of statement of this H over here. Let's see, should also talk about what this sine function does. So the sine function is, again, depending on your exact formalism of your problems, it'll do slightly different things. But sine in this book is just, say, sine of A is defined to be +1 if A greater than 0, -1 if A less than 0. And here you'll notice that the sine function actually has no definition when A equals 0. So it's undefined. For A equals 0, and this is sort of a maybe a notational weakness or shorthand of the textbook that if they had changed one of these to be greater than or equals than, then most of their statements would be like more fully correct. But the understanding is here that like nobody cares about the case when something comes out to be exactly 0, so we'll just use greater than or less than. So the takeaway from that is no one cares about A equals 0. And so if you ever are in a situation where you see like, oh, somehow I'm getting a 0 inside of the sine function, then you're in a situation where just nobody cares about that. And so you can make it go +1 or -1, whichever one you want. This formula up here, super wieldy, super unwieldy. So let's make it more wieldy and rewrite it as sine of W transpose X plus B, like that. They'll use both of these two different versions throughout the book, or especially this first chapter. And again, I don't think I mentioned this right here, but these subscript i's are meant to be indexes into the W and indexes into the X, not not vectors, not determining which one in a data set. I know that their index is into a vector because we're going up to the D dimension here. D is the total number of indexes. It's the total size of the W and the X. If this was a capital N up here, then I would be starting to think about these being the individual data points. So this is equal to sine of W transpose X plus B. Even this though, even this statement right here is a little bit more unwieldy than we would like it to be. And so we will basically always write this as, and I didn't give myself quite enough room right here. So I'll come down right here. H of X equals the sine of just W transpose X. And here, this W and this X are different than this W and this X up here. And in particular, the way this W and X are related is we say that W will take the value W1, sorry, WB, and X will take the value X1. So now these are both R to the D plus 1 dimensional vectors. The D comes from the fact that we have the W and the X over here in our vector. The plus 1 comes from the fact that we added the scalar B and the scalar 1 right here. And now if you work out the dot product between this new W and this new X, you get the same thing as you had up here previously. So always be writing things like this, W transpose X, with the understanding that this X isn't actually the X from the data set. It's this sort of modified thing that has this additional 1 down here, so that we get this W transpose X plus B. The perceptron hypothesis class is the set of all functions of this particular form. All functions, all of these H functions that are somehow the sine of the inner product of these two vectors right here. The X, again, is the input to one of those data points, one of those functions. This W here is what defines which one of those functions we're a part of. I'll draw some pictures of all of this in a second. If that's not feeling concrete enough, then we'll get a little bit more concrete here in a bit. But any questions about the notation? Okay, so describe which features for the bank loan problem are likely to have high weights and which features are likely to have low weights on a good perceptron hypothesis. So again, there's many of these H's. Which ones are going to be good ones for our particular problem or bad ones for our particular problem? Well, if we have, so we mentioned before that one of the things that we expect to be correlated with being a good loan candidate is somebody's total assets. So W total assets. I would expect that to be very high and positive. Maybe say high and positive, but something like the total debts, I would expect that to be negatively correlated with whether somebody is a good loan candidate or not. And so with we're multiplying their whatever number of their debts are, maybe they have $1 million in debt. I want to multiply that by a negative number, maybe a large negative number, so that the sign will end up being the right direction. So the sign will end up being negative, and we won't approve the loan.
Yeah. A large negative, so we did that.
So yeah, here, so by the down arrow, I just mean that it's a very small number, and small, I don't mean close to 0, I mean negative. So if yeah, maybe just writing plus and negative is, so very, very large, very, very negative, very positive, very, very negative. And by very, I don't know what very means. 1 might be a very positive number. 1 million might be a very positive number. Just really the positive and the negative the direction is the most important thing. And same like the income, probably positive, and then the marital status, probably positive. But again, our goal is not to just like sit down and decide what should be the optimal of these W values. Our goal is to somehow use like all the past data that Wells Fargo's made millions of loans to people. And so they have lots of data about what loans they made money on and what loans they didn't make money on. And they want to get these weight parameters very fine-tuned into the right slot so that they make the most money. Any questions so far? Okay, so pictures of good and bad examples of the perceptron hypothesis class. So fixing the dimensions D to be equal to 2. I'll draw a bunch of plus arrows for positive data points and negative arrows for negative data points. What we mean by a good example of a hypothesis would be a line that directly separates the pluses from the negative. That would be a good one. That's going to have, if this is our H where we divide like this, everything to the left-hand side is going to get assigned a plus, everything to the right-hand side gets assigned a negative, then we're going to be doing really good while we're classifying things. If we instead had something that looked like this, that just sort of split things in a wrong direction, this would be not a good one. This would be a bad hypothesis class, no matter which side I assigned the positives and the negatives to. We're getting things in the wrong directions here. So our goal is going to be to have an algorithm that somehow starts with one of these bad hypotheses, and it's going to get us into a good hypothesis. So our goal, again, whilst we're doing this learning procedure, we'll start with a bad hypothesis and then maybe somehow rotate this bad one into being a good one like this. At this point, this blue data we would call linearly separable. Because there does exist some good one of these perceptron hypothesis class. There does exist some good straight line hypothesis. There does exist some good that says hypothesis right there. Not all data is linearly separable. And so if, as an example, we just had all the positives in the middle and then a bunch of negatives on the outside like this, no matter where you draw your line, you're not going to get, even if we have, say, pluses over here, we can't get everything classified perfectly. So every hypothesis is somehow a bad hypothesis here. So this data down here, not linearly separable. And as we start here, as we start talking about our perceptron algorithm and our runtime, we're going to be assuming that the data, at least our initial assumptions will be that the data is somehow separable like this. And so there is some good hypothesis for us to get to. Any questions about any of that? Yeah.
Is there a way to quantify whether it's a good or bad hypothesis?
Yeah, the question is, how can we quantify whether it's good or bad? And the answer is that we could count how many of these, like in the best possible hypothesis, how many are we getting correct? And the second chapter of this book goes into detail on that.
But it
So we'll get there.
does it have to be like all the values correctly classified, or as long as it's like overwhelming majority?
At this point, it's has to be perfect. So our G function, the thing that we're finding, not only is it going to be approximately F, it's going to be exactly F when we're done with it. So write that out. Our G for now will be exactly equal to F when we're done. None of this like approximation stuff. Okay, and so this first learning algorithm that we'll be looking at is the perceptron learning algorithm, the PLA. Probably nobody here thinks of the People's Liberation Army when you see the PLA, but I always think of that when I see the perceptron learning algorithm. I can't get that out of my head. But so state the PLA update rule from equation 1.3. Here, another confusing thing about the notation in this book. Make sure I copy it down exactly as they have it here. They use W t plus 1 equals W t plus y t times xt, like this. Here are these parentheses. They look like function application. This is not function application. And it's not multiplication. It means that like this thing right here, x parenthesis t, this is the tth data point. It's different than x sub t. Different than x sub t, because at each iteration, we'll select, and so a data point pair xt, yt, that is currently misclassified. Doesn't matter how you do that selection. You could select it randomly. You could go in order. You could just take the very first one. So this t right here corresponds to the actual number of steps that you've done so far. If it was a subscript, then it would somehow in the order of the data sets. But the way that you select it doesn't actually matter. So that's the iteration update rule here. And also it's recursive, so we need our base case w of 0 just being equal to the 0 vector. And it turns out that as we apply this rule, we're going to get closer and closer to one of these good hypothesis classes. And so we will first justify why this is maybe a reasonable update rule. We'll see how it's moving these W's closer and closer to the ideal hypothesis class. And then we will talk in detail about the runtime. Good question. So the question is, what exactly are these T's? The answer is they are not the index. It's not the Tth data point. It is not the T index into the vector. This is on iteration T, select one of the data points, and it's that particular thing that you've selected. So T here standing for time. Yeah, like time step. Good question. Any other questions so far? Okay.
So you're multiplying y t like at that t equals to...
Yeah, so this yt and xt, each one of these two things by themselves are like, those are the two components of the data point, and then they're multiplied together. So yeah, that's just physically like, or notationally what's going on. Let's think about some of the intuition about like why is this maybe going to be a good thing to do? That if we have our hypotheses like this, each one of these hypotheses, each one of these possible lines, again, corresponds to one of these G functions, which corresponds to an individual W. And how is updating the W's in the way that we've just talked about going to be moving a bad hypothesis, at least in the direction of a good hypothesis? That's what we're going to take a look at. So in the book, they have both exercises and problems. Exercises are sort of spread throughout the chapter, and then problems at the back of the chapter. So here we're going to go through exactly what exercise 1.3 is in the middle of the chapter, and we'll the goal of this is that it will hopefully give us some algebraic intuition into why this is a good update rule. Maybe it won't be like geometric intuition, but it'll be algebraic. We'll see why it's good. So here, when we do the y, t, wt, xt, yeah, it's just a random formula for us. We'll say why is that going to be less than 0? And first of all, we know that the data point xt, yt is misclassified. Why do I know that? Why do I know that this data point right here is guaranteed to be misclassified? So this statement here is going to be true for all time steps, whether it's time 0 or time not 0. The reason that it's misclassified is just by definition at every iteration, we select xt and yt so that it's currently misclassified. It's just the definition of how we selected the next data point to look at. Whatever data point we're looking at next, it's going to be misclassified. So I know it's misclassified. And because it's misclassified, I know something about the sign here. I know that the sign of W transpose T x of T like that, I know that that's not equal to the y of T. So if something was correctly classified, again, here is my prediction formula. This is one of those h of x's. We had that the h of x equals the sine of W transpose times x for some x. So this over here is my my hypothesis, the thing that I'm testing. And if we had a good h, then we were going to get the same sign back. But we have a bad h, so we're getting a different sign back. So being misclassified in this thing over here, not being equal to the y, that's just sort of definitionally the same things. And so there's two options about how this can happen. Two options. If y is -1, then the W transpose T W transpose T x of T like that. So this thing over here must be negative because they're not equal to each other. And if they were, if the y is positive, so if that's, sorry, that's a positive right there. If the y is negative, then this thing over here must be positive because we know they're not equal to each other. Just being the definition of the misclassification, they're not equal to each other. And so the only options here is that y is positive, that whole thing is negative, or that is negative, that whole thing is positive. Either way, we have one positive, one negative. Multiplying them together up here. This is the y, w, x, multiplying them together makes us less than 0. So no matter what, the y, t, wt transpose, xt must be less than 0. Any questions about that? Yes. Why does the weight transpose not have a sign?
Yeah.
I'm not sure what you mean by that.
I mean, we know like the extreme rights is that just classified, but we don't know. I feel like, and then like think the weight of like the weight transpose XT, which is just like the next level. I mean, we can just think about it. It's just I'm just asking why we don't have like a sign of XT, YT, have like YT transpose.
So questions about the sign of W and the sign of X. Both W and X are vectors here. And so a vector can't be described as having a sign as being positive or negative. We have to take the inner product between those vectors to get down to a scalar number and get a sign about from that scalar number. So the only thing that from like just a sort of the type perspective, we can only take the sign of W transpose X, can't talk about the sign of W and X. Yeah, I'll emphasize again that this thing on the left right here, this is one of our instances of the hypothesis of one of these potential G functions. It's a little bit confusing that we have the G's and the H's. The H's means that it's a family of functions. The G is the function that we're particularly trying to learn, getting to eventually. But in this family of functions right here, we're doing this transpose W transpose X and taking the sign of that. And if it gives us the right thing, then we're good. We want to get the right thing on everything. We want this to be equal to y of t everywhere. So we pick one of the values where it's not equal to y of t, and then this is the result, that this value right here happens to be negative. The second part down here. So again, it's all very, very abstract, just a whole bunch of symbols. We're getting to the point where we can get our intuition, our algebraic intuition. We're going to show that this little formula right here is greater than this formula right here. And why might we want to do that? Why might we care to do that? That it'll turn out that at every iteration t+1, if this value is getting greater than the previous iteration, then we're getting closer to the right solution. So let's work through the details here, just plugging in our definitions, getting a little bit more comfortable with these definitions. So we want to show that this thing on the left greater than this thing on the right, this WT of t+1, we know by definition that that's equal to what? We go up to our iteration rule, WT+1, WT plus YT, XT equals WT plus YT, XT. That's from the definition of the Perceptron learning algorithm iterations. And so plugging that into this formula up here, YT of the WT+1, WT plus Y, T, X, T like that, transpose, and then the X of T. So this thing right here corresponds to that after substituting the value for WT plus 1. Working through the multiplications, the math right here. Y T times W T transpose times this X of T. So this first term is that W times this X. And then the second term over here plus this Y times this Y. Y T squared. And then this X times this X. X transpose T. X of T like that. Over here on the right-hand term, that has to be positive because it is a square of something. So that's going to be a positive number. This thing over here, also positive because it's anytime you have the inner product of a vector with itself, it's going to be a positive number. So this whole thing on the right is going to be positive. And this thing on the left, call this the right-hand side of our equation right here. That's equal to the right-hand side right here. And so we are this thing, this term right here is greater than or equal to that plus a bunch of positive stuff. Yes. WT plus 1. This right here. This up here. So the W of T plus 1 equals WT plus YT XT. No transpose. Thank you. Again, at this point, trying to get the intuition more familiarity with the notation, but any questions? So going from this line right here to this line right here, the first left-hand side is that Y times that W, that X times that W is that right there, the red part, and then that Y times that term, that X times that gives us the green part down here. So the Y times W times X, YWX, and Y times Y, X times X, YY, XX.
Is there a letter for, like, what is the backwards T? What is the name for that?
The backwards T is just how I write a T.
Oh.
Nope. Good question. Yeah, I don't know why everybody else writes it backwards and I write it forwards, but yeah.
So I guess how you multiply the y to transpose to that not take into account.
And then everything in the parentheses right here is transposed right there. So the W's, that W gets transposed, that X corresponds to this transpose right here.
And the y does not.
And the Y's are just scalars. They're just the plus ones or negative ones.
Okay.
Okay. So now how is this like meaningful for us? How does this tell us that we're going in the right direction? Well, if we recall that our hypotheses classes look something again like the sine of W transpose X. That is what our family of H's looks like. And we started off negative. That was what part A was saying. And then part B up here says that we're getting more positive. We're adding something to this term right here, that the WT plus 1 WT plus 1 is somehow bigger than the WT. So we're adding stuff, adding some number on each iteration. And that's going to make this sign of WTX go closer and closer to what the sign actually should be. It might not get there in a single step, but it's getting closer. So it's making it, adding stuff to something negative makes it closer to positive, if not positive. Eventually, for our G value, everything is going to be positive because there's no misclassifications. So for G, everything is going to be positive. Each iteration, we're finding one of these things and getting it closer and closer to being positive. I'm going to jump over here to a picture of the textbook in a second. So this figure on the bottom of page 7, which does a little bit more geometric-ish intuition of this. That if we've selected some particular point, then we're moving this hyperplane closer and closer to that point, eventually rotating it. So in this case, it'll be vertical up and down. Okay, the most important part of this is actual convergence. Like, what is the runtime going to be? So that discussion above, maybe it helps you think a little bit more about why it seems reasonable. But now we're going to talk about the actual like rate of convergence. In this class, we're not going to prove anything about the rate of convergence. So problem 1.3, the textbook has problems at the end of the chapters, exercises in the middle of the chapter. Problem 1.3 at the end of the chapter would ask you to prove this bound right here on the number of iterations. We're not going to do that proof and just accept that as given and somehow try to understand the consequences. When we talk about that, we'll compare some of the features of this runtime bound that we'll get to the runtime bound of the PageRank algorithm. So first of all, there's a lot of terms inside of here. There's R squared, W squared, rho squared at the bottom. That Greek letter right there is rho. And let's sort of illustrate what exactly we mean by each of these terms. Draw. In the previous drawings, I didn't have any particular set of axes. In this case, I'll draw a particular axis right here. That's our origin. And if we have data that looks like some pluses over here and say some minuses over here, we can put some on this side too. Then this R right here stands for the radius of the data set. And it's just like draw a circle, the tightest circle that you possibly can. That is actually a circle. And that distance is the radius. So this over here against the L2 norm, you look at the L2 norm of all of these different data points, all these pluses and minuses, and make that as tight as you can, whatever the largest of those values is, and that's our R value, often called the radius of the data. This W star, so I'll draw another different data set over here. Make it look kind of similar. Plus, 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 a whole bunch of minuses like this. And then the W star is intended to be any of these optimal lines separating the pluses and the minuses. So I could draw one like that. That seems like a relatively reasonable one. Again, previously I was talking about each of these lines as being an individual, like H in our hypothesis class, an individual one of these functions. But these functions are uniquely determined by their parameters. So I'll write that out. H is uniquely determined by W. And so we often use the H's and the W's interchangeably, depending on whether it's more convenient to talk about it as a function or more convenient to talk about it as a vector. And so here, this H would also be equal to W star. I'll say H star equals W star. In general, whenever you see a star on a variable, it somehow means like it's the best of its kind. A star means somehow it's the best. In this case, the W star or the H star is not unique for this particular data set. There's many of these lines separating the pluses and the minuses that I could draw. Like that one right there is also an example of a W star. Either one of these would be perfectly valid separating hyperplanes. And in this formula up here, they're just talking about a separating hyperplane. It turns out that this bound happens to be true no matter which one of the separating hyperplanes you select for it. So doesn't matter which one, any of them is fine. The last quantity right here, this row, it turns out, see, I'm going to use orange here. That rho is a measure of the distance between the separating hyperplane and the data points. And if you work out the math, oh, come on. This distance, whatever the shortest distance from the your separating hyperplane is to the closest data point, that is equal to rho divided by the norm of W star. And so as rho increases, the data points are somehow farther and farther away from W star. This value of rho is dependent on your W star. So here I have one for this hyperplane, and then I'll draw another one like this for this hyperplane. That would be that's also equal to rho divided by the norm of W star. But here, this W star is that one. Here, this W star is that one up there. Any questions about, yes? Yeah, the question is, for this R, does it have to be around the origin? That maybe you have a data set that would look something like bunch of pluses, a bunch of negatives like that. The R value is still centered around the origin. That's still the radius of our data set like that. So for most of these pictures, it doesn't matter like where the origin happens to be located at, but for the R value, it does. Good question. Any other questions about these things notationally? Alex?
For the row, we're just looking at the distance from W star to the closest data point on any of the
sides of the line?
Yeah, that's a great question. So here I happen to draw these little distance indicators between W star and the negative data points, but it's whichever one's the closest on either side. So maybe actually for this one right here, if I drew it to scale, then this is actually the closer distance than this one right over here. So it's the closest on either side. I'll draw one more picture to make that clear, that if we have, so here's our star, our negatives, our pluses, and this is a valid W star, then that distance right there is the rho divided by the norm of W star, the margin of our data points. And yeah, sometimes called the margin, the distance between the line to the data point itself. And so somehow our runtime is going to be related to these various properties of the data sets, and by this particular formula right here. We'll finish up this B problem right here, and then we'll pause until Wednesday. So what is the overall runtime of running PLA to convergence? Well, this is the total number of iterations that we're going to have to use, t less than or equal to this thing over here. Each of the iterations involves a single linear product or a single inner product. Involves a single inner product the W transpose X. Those are d-dimensional vectors right there. So that runs in time, actually theta of D, the inner products of d-dimensional vectors, runtime theta of D. And so then if we have t iterations, then overall runtime would be equal to say theta of t times d, which will be O of the d r squared norm of W star divided by that squared divided by the rho squared. Had to switch to the big O notation instead of the theta notation because up here on the formula right here is a less than sign, is not equal to that. If our initial vector just or if our hyperplane happened to go through the origin, then we'd be done without doing anything. But that's going to be the d dimensions. So each iteration takes time d, and then that number of iterations. On Wednesday, we'll talk more about that, visualize more of these properties and compare them to the PageRank. But that's it for today.